Jean Dieudonné once wrote that there were three innovations which launched combinatorial topology. One is the barycentric subdivision, the second the use of incidence matrices, and the third duality. In this exposition I want to address all 3 points. So first of all, barycentric subdivision. We will look at it in the context of graphs, and where incidence matrices define a Laplacian. We look at the eigenvalues of this Laplacian, look at the spectral theory, and formulate and prove a theorem. And then we look at barycentric characteristic numbers defined by this process. This is part 1. So we have a graph G. Assume it is a finite simple graph, meaning there are finitely many vertices, finitely many edges, there are no self-loops and no multiple connections. And we define from this graph a new graph which we call G1. So V1 is the collection of all cliques, complete subgraphs of the graph, and E1 is consists of all pairs of such subgraphs where one is contained in the other. So let me give you an example. So we have a graph here. Example of a graph. It's finitely many vertices. And edges, and we look at all subgraphs, complete subgraphs, and we mark them with a new point. So here, for the edges, we get new points. And then there's also a triangle which gives us another new vertex, and now we connect two points if one is contained in the other. So in this case, this triangle contains all the vertices, so we connect them, and also contains the edges, so we connect them. And so this is the first barycentric subdivision. We can continue that, and you see the spreads part of the blackboard already, triangle which has been subdivided 4 times. So we can continue that, right? We get G2 and so on. We get Gn, which is Vn, En, and in each case we get a finite simple graph. And this barycentric subdivision has nice properties. Maybe I just list them informally. First of all, what we have is that the dimension is just the average of the dimension of the unit spheres plus 1, the inductive definition. So that the dimension of G1 is bigger or equal to the dimension of G. That's true in general for any finite simple graph. For geometric graphs, which we talk about later, there's an equality, the dimension stays the same. We have also, we can write actually G1 as a product, G cross K1, using a Cartesian product, which is algebraically defined using the Stanley-Reisner ring. And we can also define a geodesic flow, G1 as a geodesic flow, or billiard, which in general is not the case. If you have an odd degree vertex, there is no natural geodesic flow, but it has a nice geodesic flow. There are other things. So G1 is homotopic in a sense which we are going to look at. It's even homeomorphic to G in some sense. The Euler characteristic, for example, stays the same. The Betti numbers stay the same. Homology stays the same. Euler characteristic stays the same. So there are lots of nice properties for this barycentric subdivision. Next, we look at the Laplacian of a graph, which is defined by the incidence matrices. Incidence matrices are just discrete analogs of divergence, gradient, curl. Just they have been introduced by Poincaré. And the Laplacian even much before by Kirchhoff in the 1850s. So this is part 2 about the spectrum. So we have a graph, and then we call L the Laplacian. This is the Laplacian. So P is the diagonal matrix which contains all the degrees in the diagonal. So this is degree, vertex degree, diagonal matrix, and this is the adjacency matrix. So, for example, if we have a graph here, triangle, and L has just each of the vertices has degree 2, and then they are all connected with each other. So there's a -1 here, -1, -1, -1, -1, -1. So this is the Laplacian. It can be written as d star d, which is just the divergence of the gradient. So d is the exterior derivative on zero forms and functions, and d star is its adjoint. And so these are the incidence matrices which Dieudonné has mentioned. And so this is a very natural object, and so the eigenvalues are like the Laplacian of the eigenvalues of the Laplacian of a Riemannian manifold. They are non-negative. So we have lambda 1. So lambda 1 is equal to 0 always. There is an eigenvalue 0. Actually, they are k connected component. There are k eigenvalues 0 by Hodge, discrete Hodge theorem, which is true in full generality. So this is lambda 1, and then we have smaller than lambda 2 ground state. The first, this is an interesting, then lambda 3 until lambda n. These are eigenvalues. Eigenvalues of this Laplacian. So now what I'm going to define is a function which I call a spectral function, which is f of g. So f of g is defined as actually I put the g in the index here, and then take x. This is a number between 0 and 1, so it's a function which gives me lambda of nx, where this is the integer. This bracket means the largest integer smaller or equal than what is inside, and so we have this is a function now from 0 to 1, and it's a step function, right? Because we have so it's constant lambda 1, and then lambda 2, and then lambda 3, and then lambda 4, etc. So we have this step function here. So this is the graph of this function f. And I'm doing that so that we can talk about different spectra simultaneously and graph them in the same on the same picture. And now what we are interested in, what happens when we take the barycentric subdivisions, and what happens with the spectrum. So and here is already the theorem. Theorem 1. So what happens is, under barycentric subdivision, so it doesn't matter what graph you start with, any finite simple graph you start with, and then you take this barycentric subdivision, this function here converges in L1. If you look at the measure here, L1, 0, 1, in this norm, it converges to a universal function fd. So fd is universal, depends only on the click number, where fd is universal, depending only on the click number d plus 1. D plus 1 is the largest, is the size of the largest complete subgraph which we have. By the way, that's also the chromatic number of the graph after subdivision, because you can always take the dimension of the previous, you know, that every vertex has been a simplex before, so that dimension is actually the color, and you can see that so the chromatology is very easy for these subdivisions. So that's the theorem. And it's very interesting, and you know, we almost don't know anything yet what is really going on here. The only thing which we know, what happens in d is equal to 1. If d is equal to 1, so that's the case when we have no triangles. That's actually what most graph theorists would kind of do when they do barycentric subdivision of a graph, because for most graph theory in the 20th century, a graph is a one-dimensional simplicial complex. And it's a shame, because graphs have much more structure. They have a simplicial complex, which is the Whitney complex, which is much richer. It's the largest complex, which they naturally come. This complex comes naturally with a graph, and you can do geometry with graphs very easily. And the language of graphs is just much simpler than the language of simplicial complexes, in my opinion. But maybe more importantly, the computations on a computer are just so simple in a graph, because they are already built in a computer algebra system as a structure, as a data structure. So you don't have to build it yourself; it's already there. So if there are no triangles, you know, like a tree, or so this is an example of a graph which has no triangle. So if you take a graph like that and you refine it again and again and again, what happens with this, the fd is explicitly known. So the fd is, you take the fd, or f1 is just 4 times sinus pi x half. So you have that squared. So that's the function which you get in this case. The universal limit. It's an interesting function, by the way. So this spectral function here, if you take the inverse of this, so the f inverse, you can invert this because it's monotone. The f inverse is called the integrated density of states in the mathematical physics jargon. As an integrated density of states. Actually, a probabilist calls this the cumulative distribution function. And the derivative of that, so that's the density of states. It's a measure. That's what the probabilist would call the probability density function. And so this is this of course this converges then here we have this converges, and also the density of states, this converges weakly, a weak star convergence to a universal density of states. And in this case, this density of states is the arc-sine distribution, which is very important. It's the equilibrium measure on a Julia set. Happens in the case d equal 2 already. We don't know what actually happens. So there are already gaps appearing. So there are gaps. And the graph is, I'm just actually sketching the gap here. The graph in 2 dimensions already starts to look self-similar. Here there's a self-similarity. You know, if you actually look at this function here, f1 of is equal to t of f1 of x, where t is the function, is this quadratic polynomial, x times 4 minus x. So that's the polynomial which belongs to the Julia set. So that's part 2. That's the formulation of the theorem. Call this universality because it doesn't matter which graph you start with. It's like in probability theory where you start with a random variable and you start adding random variables, and you take random variables and you take 2 copies of the same random variables, and then you normalize it, and you do that again and again and again and again. What happens in the limit? You get to the Gaussian distribution. So you get to a limiting. It's the central limit theorem. And that's similar. It's just much easier. It's even much easier than in the case of probability theory. It needs a little bit of linear algebra. We have to kind of perturbation theory. And it looks difficult. But I was lucky enough that I could take in 1995, I could take a course on trace ideals, which Barry Simon gave, and so he talked also about the theorem of Lidskii, which is very beautiful. I'm lucky that I know this. So this is sort of the proof. So this is the next thing, so the proof. But the proof so there is a theorem of Lidskii, Russian mathematician, which says that if you have 2 self-adjoint matrices A and B, actually symmetric real, and if you look at the eigenvalues, so lambda 1 until lambda n, alpha n are the eigenvalues of A, and beta 1 until beta n, the eigenvalues of B. Then you can look at also the eigenvalues of A minus B. So this is gamma 1 until gamma n. So these are the eigenvalues of A minus B. The symmetric real matrices, so the eigenvalues are real. And we can look at the L1 norm of the differences. So we can look at the sum j equal to 1 to n, and then we take alpha j minus beta j. And what Lidskii showed is that this is smaller or equal than the sum j equal to 1 to n gamma j. Beautiful theorem. It's proven in the book of Barry Simon on trace ideals, and but it's not yet, cannot be used yet very well. I mean, what is nice is there's a nice addition of which I learned from theorem last, which makes this much more powerful. Namely, that this one we can estimate with the entries of the difference, and so we have the sum j equal to 1 to n, and then alpha j minus beta j is smaller than equal to the sum. And now we take all matrix entries a, j, a, I and j goes from 1 to n, and then we take C, let's call this C here, and then this is C I j. So this is really made for graph theory, because if you take a graph, if you take a graph and you delete one edge, if you delete one edge, what happens is this is a perturbation of the graph. You modify the graph by removing some edges. What happens is if you look at the matrix, so the matrix before and the matrix after is, if this is the edge E I J, this is I and this is J, then you have just that the I and J and I, J. So you have only changes here at these 4 entries of the Laplacian. This is the Laplacian here, and you remove this edge. What happens is you actually you change this by 1, you change this by 1, you change the diagonal entries also by 1. So there are 4 entries which are changed by 1, and so you can estimate the difference of the sum of the difference of the spectrum of the eigenvalues with in terms of the number of edges you have to change if you go from one graph to the other. So this is a very nice application of this Lidskii theorem for graph theory. And now what happens when we do a barycentric subdivision? You see that here in this graph. So you have you start with a triangle, and then in the next step you have 6 triangles. You have in general you have just p plus 1 factorial. You know, the maximal simplices d plus 1 vertices. There are d plus 1 factorial parts here. So in this case we have 6 triangles. And what happens under the subdivision? Now this gets again subdivided into pieces. Each of them gets subdivided into pieces. This is the subdivision of this triangle. But if you look at this, now each of these triangles again gets subdivided again and again and again. What happens is the interface here, which is the boundary, is increasing much slower than what happens inside. So what we can do is we can take this apart. You know, we take actually, and this we take this 6 pieces or d plus 1 factorial pieces apart, and if you take that, if you make this modification, if you take it apart, so if you take it apart and look at the evolution of the barycentric subdivision of each of this graph where it is separated, then here the function, if this is the graph G. So if this, the spectral function of this graph is the same than the spectral function of the triangle. What there is an error which depends on the boundary only. Now what happens is the boundary grows much slower, actually exponentially slower than the inside. So you just look at that in the next section, and in the limit it becomes indistinguishable. So this part goes away. The reason is if you look at this function here, and so this size is 1 over n, so we have the L1 norm of f is just 1 over n times the L1 norm of the eigenvalues. And that's the little L1 norm, which is actually just happens here, which appears here in Lidskii theorem. So if you divide by n here, you have actually here, you actually talk here about the L1 norm of this of the difference. And this is small. This is 4 times then the number of edges in the interface, in the boundary, but that grows much slower. So every time d plus 1 times slower, and so this goes away exponentially fast. So that's the. So what happens actually is this map is a contraction. If you adapt the norm, it's a contraction, and you can use the Banach fixed point theorem in that L1 norm. The functions don't stay bounded. What happens here in the case d bigger than 1? In the case d equal to 1, the degrees always stay 2, right? If you do barycentric subdivision, the degrees always stay 2. They don't grow, but here the degrees grow, and they grow exponentially. So what happens is this function actually in the end will be in L1, but it will be unbounded. And so it converges. This convergence of is uniform just by general real analysis. This is uniform in each compact interval inside the open unit interval. So that's very nice. This convergence is very fast, and you observe that also numerically. So we look at the number of complete subgraphs of a graph and see how they change. So in the algebraic or combinatorial topology jargon, one calls this f vector. Let's look at that. Let's just define this. So let's just call vk of g. So this is the number of k plus 1 subgraphs. So in graph theory they are called cliques, these subgraphs. In topology it's often called faces, algebraic topology. And so these are this number of faces. That's the so V0, for example, that's the number of vertices, and V1 is the number of edges, and V2 the number of triangles, etc. So this is and then we can look at the vector. So V is of G, V of G, that's just call it V0, and to VD, where D is the clique, D plus 1 is the clique number. So this is the that's called the F vector, clique data, depending on language. So now what happens with the under subdivision? So there's a little lemma here. What happens is this clique number, clique vector of the Paricentric subdivision is just A of V of G, where A is a matrix. It's a universal matrix. which doesn't depend on the graph at all. And a little bit embarrassing, but when I was studying this, I was studying this experimentally, and actually, kind of looked what is kind of the best, what is the best matrix which fits this. So I took hundreds of feathers, random graphs, and just made data fitting, and found and then it turned out that it's actually just exact. There's an exact matrix which does that. Here is kind of the number. So A is a matrix, it's upper triangular matrix. It has ones, and then it has 0. So in the diagonal they are just a k factorial. And then the next is 0, 6, 36, 150, 0, 0, 0, 24, 240, etc. So you have this matrix, and so of course like anybody, when you look at that, you look at it first for small dimensions, and you get the recursion. In this large dimension, you get recursions, and so on. You solve the linear algebra in each case, and then you get tired. And so it's kind of nice that there is a universal matrix which does that. Actually, it is, as I later found, it is known. Somebody wrote even it's well known, even so it doesn't appear in any book I find. Maybe in Stanley's book there's a version similar to that. And so the A, I, J, this is I factorial. And then there are the Stirling numbers, J, I. These are Stirling numbers, the second type, second kind. Which, for example, tell how many equivalence classes with I elements there is in a set with J elements. So it's a combinatorial number, like the Bernoulli numbers, quite important in combinatorics. So when I derived this matrix first, I actually got the recursion. I got each, constructed column after column recursively, and essentially kind of rediscovered this recursion for the Stirling numbers. So what happens, essentially, say if you, for example, you want to know how the number of triangles grows, so the triangles. So each triangle gets multiplied by 6 each time. But then what happens is if you have a tetrahedron running around somewhere, the tetrahedron also on the barycentric refinement produces triangles. And so for each of the tetrahedron you get 36 triangles. And so you can actually compute this recursively, because you can look at the boundary, and so which brings you one dimension down. So you can recursively actually compute these numbers, and that's what I did first. But this is a beautiful formula, and for this barycentric matrix. So this gives you all the answers which you want to know. How many triangles are there after 100 steps? You can compute that. Even so, you cannot compute the barycentric refinement, because that's just too many points. So the eigenvalues, the eigenvalues is clear because it's upper triangular, right? So this is very nice. And now we come to the important definition of a barycentric characteristic number. So let's look at an eigenvector. So if AK is an eigenvector of AT. Of course, AT has the same eigenvalues to the eigenvalue k factorial. Then we can look at this as a functional on graphs. Right? We can look at x of g. So g is a graph, we can define this, and we just take the dot product of A, so this is our function of xk, is ak, and then we dot it with this f vector with, let's just write it in this way, is a bracket, and then v of g. So let's see what happens on the barycentric subdivision. If you take xk of g1, then we have ak, then v of g1, but v of g1 we know is a of vg, right? That's a of vg. And now if you take the matrix on the other side, we have to take the transpose. So this is at ak v of g. And it's an eigenvector, right? We know it's an eigenvector, so this is a k factorial times ak vg. And so it's k factorial times xkg1. K factorial of xkg. Isn't that nice? So we have now seen that this barycentric, this I call this barycentric characteristic number, what happens if you do a barycentric subdivision, the number gets multiplied by k factorial. So they explode in general, except the k equal to 1. The k equal 1 stays. So k equal 1. For k equal 1 we get an invariant. Now you can guess 3 times which invariant it should be. Actually you can guess it the first time. And of course it's the Euler characteristic. Indeed, A1 is just the vector 1, minus 1, 1, minus 1, 1, minus 1. So if you would not know about the Euler characteristic, this would be the first, I mean this would be the moment where you actually get it. It seems that Descartes was the first who really saw the Euler characteristic, and was so paranoid that he wrote it in a secret notebook, which then Leibniz found later, and then Euler of course then proved the famous formula, right? V minus E plus F is equal to 2, and then it's almost a comic story about this theorem, because this theorem got disproven again and again, because this is not always true. So and then also generalized to higher dimensions. It's a very interesting story, the story of the Euler characteristic. But it's in any dimension. So there's this Euler characteristic. Now that's why barycentric characteristic, because of the Euler characteristic. So this is x1 is the Euler characteristic. So this is invariant. The Euler characteristic is now immediately invariant. You see here it's invariant in the homotopy, and it's invariant under this barycentric. It's the only invariant, and that has been proven countless times in the past, and that's the easiest way to see that it's actually the only general invariant, obvious invariant. Now, of course, when I looked at these numbers, I was computing the numbers for many examples, and especially for discrete manifolds, or discrete, S2 cross T2, all kind of different manifolds, orientable, non-orientable, projective planes, all kind of things, just to see what happens. But there was an amazing thing which happened, is that if you take a graph G, which is a D graph. D graph, I call it D graph like a D manifold. It's a graph where every unit sphere is a sphere. It's kind of a discrete manifold, and so if G is a D graph, triangulation of a manifold, of a D-manifold, compact D-manifold, and then what happens if K plus D is even, then I saw that xk of G is 0. Of course, if it is 0, then it remains 0 under a barycentric subdivision. So then it's an interesting number, and let me formulate that theorem and then prove it. So these are the barycentric numbers. I mean, they turned out to be, did not know it when I found out that they are known under the name Somerville-Clay invariants, not in this form, completely different way, and but it's essentially you can deduce one from the other, and the proof which we are going to look at is completely different. Actually, I got this proof before I really knew that this is no. Let's just look at the theorem. I formulate the theorem. To formulate the theorem, I have to say something about D graphs. So graphs which are discrete manifolds. There are many versions of that in combinatorial topology. Some assume some local cohomological triviality. So the notion of D graphs makes this very, very clear, and it's actually just within graph theory. We are not digressing into the continuum, like looking at triangularizations of a manifold, or take the topological realization of the simplicial complex and actually look at the corresponding manifold and assume something about that manifold. So this definition which I'm giving now is completely graph theoretical, can be understood and appreciated also by somebody who doesn't accept the real numbers. So so first of all, some notation. So G is a graph. So again, V E, finite simple graph. And so if X is a vertex, we can look at Sx. And I just call this the unit sphere. So again, there are other names known under it, but it's very intuitive, right? You have a vertex, and you have, if you look at all the, so in this case, the unit sphere is, so this is a subgraph generated by all the vertices which have distance 1 to the graph. In a social graph, these are all your friends. But it's a graph, it's not just a set, it's a graph. It has the unused the edges. Two are connected if they have been connected in the original. And then we have also, yeah, so this is the unit sphere. And so now we have to say what is a sphere. And this also, for me, emerged over years. It turns out there's a mathematician, Ivanchenko, who's also called now Evako, calls himself Evako. So I call it Evako sphere. Or just simply a D sphere. So a D sphere is also, everything is defined recursively. So we have a -1 sphere. There's only one -1 sphere, that's the empty graph. It's usually, this is a -1 dimensional graph. And then a 0 sphere. So this is the graph which has 2 points. And what happens is that for this graph with 2 not connected points, the unit sphere is empty. So what we want is, for a sphere, is that every unit sphere in that sphere is again a sphere. So, and more generally for a D graph, we want to have, so everything is recursively defined here. So a D graph so for a D graph, every unit sphere is a D minus 1 sphere. And then we have also defined a D sphere. So a D sphere is a D graph where which when punctured becomes contractible. Let me just write it like that. Which when punctured becomes contractible. So what is punctured? Punctured means just taking away one vertex. So if you take, for example, this is a circular graph with 5, so it's also called C5. This is a sphere, a vacuum sphere, because if you take away one vertex here, if you take it away, then it becomes collapsible and becomes just a contractible graph. This graph is contractible, and we have also to define inductively what contractibility means. This is a notion also due to Ivachenko, and actually goes back to Whitehead, and it leads to the notion of homotopy for graphs. So it's very intuitive. Contractible means, so this is a contractible, so G is contractible. It's inductively defined, contractible. Let me just also call here B of x is the unit ball. Unit ball. So if Bx and if the ball and G minus the point, the punctured graph, is contractible. So for example, a triangle is contractible, right? Because you can take away a point, and the ball is the whole thing. So you can take that, just take this kite graph, and so you can take away that part, because it's still contract. You can take that away, and then you can take that away until you reach K1. So K1 is the assumption. K1 is also contractible. This one single point is contractible. So contractibility means kind of homotopic to the one-point graph. And so as a sphere, that's very natural. You take a sphere, right? If you take a sphere and you punch a hole, then it becomes a disk and becomes contractible. A disk is contractible. So this is a notion which is, everything is completely graph theoretical, and contractibility is inductively defined using the assumption that K1 is contractible, and then inductively you can build contractible graphs by just adding more vertices, and always make sure that the unit ball of the new vertex is contractible. And then a D sphere is a homotopy definition. It's a D graph where when you take away a point, it becomes contractible. And then we have D graphs which play the role of discrete manifolds. And these D spheres have all the properties you want to have. They have all the Euler characteristic of the -1 sphere is equal to 0, and then the 0 sphere it's 2, and then the 1 sphere, so that's a 1 sphere, for example, it's 0 again, and then for a 2 sphere, like the octahedron is the smallest 2 sphere, it's again 2. For a 3 sphere, it's again 0, and so on. So you have all the nice. Behaves like a sphere, and it means that the graph locally looks Euclidean, that you have really a sphere structure. And it also has as nice properties, inductive properties, which are very helpful. That if you take two spheres and such a unit sphere and the unit sphere in the sphere, so it's again a sphere. So the intersections of spheres are spheres. And this allows to prove things very elegantly just by recursion. So this is a notion. This is the notion of graphs we are going to look at. We look at this. So nice triangularizations of D manifolds are the graphs. But not all triangularizations. It's easy to build triangularizations which have not this property. So it's a nice triangularization. So let's look at the theorem. Look at the theorem. So we can also define graphs with boundary. So if you take if you look at the graph which has, for example, the wheel graph here, then this is the interior because every unit sphere is a sphere. And then there are points where the unit sphere is not a sphere, but the unit sphere is contractible, or a disk more precisely. And in that case, that would be the boundary. So that's a graph like manifolds with boundary. You can define it in the same way. But let's look at the theorem. So this is theorem 2. And the theorem tells that if G is a D graph, and D plus K is even, then this case Paricentric characteristic is 0. Let me just formulate it also in the case with boundary. That's a little bit more general with boundary. Because that's actually, it's more general, but it's easier to prove because we can do induction, and often when you do induction, it's actually easier to prove a stronger theorem because the induction assumption also becomes stronger. So we take a D graph with boundary, D plus K is even, and XKG is equal to XK of the boundary. This means this characteristic lives on the boundary. And so especially if the boundary of G is empty, then XK G is. Now let me look at some examples. So for example, if K is 1, that's the Euler characteristic. So K equal to 1. Euler characteristic. Now D has to be odd. So D is odd. And this means that the Euler characteristic of G is 0. And that's well known. It follows from Poincare duality if you have an orientation. And but it's true in general. And if, let's just look at some other things. So there are some interesting cases. Kind of the first really interesting case, which is new. So I mean, let me just take K equal to D, which is kind of interesting because K equal to D gives always K plus D is even. So K plus D is even. And what is that? This is a boundary volume. K equal D plus 1 is actually the volume. And so in the case AD plus 1. Remember the eigenvectors? So this is actually 0, 0, 0, 1. So that's volume. The number of facets, the number of largest cliques. That's the volume. It's also one of the Paricentric characteristic number. But then we have AD. This is never 0 because d plus 1 plus d is odd. But take AD, which has the, we can always normalize the eigenfunctions so that they are positive first, and then what do we have here? It's minus d plus 1. So this is a interesting number, which just means that, for example, you have a three-dimensional graph, and then if you look at tetrahedra, the number of tetrahedra, and then you take the d plus 1 times the number of tetrahedra, this is equal to 2 times the number of triangles. It's just a counting. It's kind of like this fundamental theorem. This Euler handshake argument. So, but in this case, yeah, that's k plus d is equal to even is even. So what we have is actually then we have that characteristic, which is kind of trivially 0. But the first case, which for me was exciting, so let's take d equal to 4, k is equal to 2, and then we have the A2 with this vector is equal to 0, 22, minus 33, 40, minus 45. So this implies that if you have a 4 manifold and you count the number of edges, the number of triangles, the number of a tetrahedra, and the number of pentatops, so hyper tetrahedra in this 4-dimensional graph, and you take 22 times E minus 33 times F plus 40 times T minus 45 times P, it gives you always 0. Which is cool, pretty cool. And for 5 graphs, so D is equal to 5, we can take K is equal to 3, and then we have A3 is equal to 0, 0, 19, minus 38, 55, 70, minus 70. So that gives us another invariant. This is invariant for 5 manifolds. It's always the case. And so that's the theorem. Actually, when I saw this experimentally, I was very excited. I tweeted that even, and was frantically trying to find a proof for that. But it reminded of something I have done before. When you look at the Euler characteristic, and what happens in the case of Euler characteristic, there is a curvature which adds up to the Euler characteristic. And what happens if this curvature is defined for graphs, for any finite simple graph, this is defined, and if you look at it in the case of odd-dimensional D graphs, what happens is this curvature always appears to be 0. And it took me 1 year to prove this, and the proof is integral geometric, by writing the curvature as an expectation of indices, and then showing that these indices can be related with smaller dimensional Euler characteristics. So this is the thing, but that looks similar, and indeed it works exactly the same way. What we can do is for every invariant we can define a curvature, and then we can have a Gauss-Bonnet theorem, and then we have a Poincaré-Hopf theorem, and then we average Poincaré-Hopf to get a Gauss-Bonnet, and then we actually write these indices in terms of smaller dimensional characteristics. So that's the proof, and that's what we are going to do next. Let's prove the theorem. We have to verify that these Paricentric characteristic numbers are 0 for D graphs, or more generally that it is equal to the characteristic number of the of the boundary. So that's what we are doing. And there are a few ingredients which we are. First of all, we want to define a curvature for these characteristic numbers. And for doing that, let me just give you a theorem which is called the fundamental theorem. Fundamental theorem. Graph theory. I call it like that, but in a special case it has been called fundamental theorem of graph theory, or Euler handshake theorem. So first of all, we have the numbers vk x. For every vertex we have vkx, which is just the number of complete subgraphs k plus 1 of the unit sphere S of x. So this is a generalized degree. For k equal to -1, we define v minus 1x is equal to 1. That's something kind of, the unit sphere is empty, and we assign to it the value 1. So for k equal to 0, these are the number of vertices in the unit sphere. This is the degree. So v of 0x, that's the degree of x. And then for k equal to 1, v1x, this is the number of edges in the unit sphere. So it's kind of another type of degree. And what happens is, if you look at the graph, and the unit sphere, so the number of k-dimensional subgraphs in the unit sphere, of course related with the number of k plus 1 dimensional graphs here just attached. And then if you count that for every vertex, there is a handshake argument which tells you that everything is counted 3 times in the case of triangles, or 2 times in the case of edges. Let me just formulate that and explain a little bit more. So what we have is, we have a little vkx times k plus 1 is the sum over all x, all vertices, and then we take capital Vk minus 1 x. So that's the theorem. Let me just tell you, in the case k equal to 0, that it's trivial. K equal to 0, then we have v0x is the sum 1, which is obvious. The case k equal 1, that's the classical Euler handshake theorem. So v1x, that's the number of edges. It's the sum of x, and then we have degree of x times 2 here. So 2 times the number of edges is the sum of the degrees, which by the way is the trace of the Laplacian, and sum of the eigenvalues of the Laplacian. And so this is the classical handshake. It's called handshake because what happens is every edge here has 2 vertices, and so they're counted twice. And so every triangle is counted 3 times. So it's a nice result. Don't find that in graph theory books, unfortunately, but it's a nice thing because it allows us to interpret to get a Gauss-Bonnet theorem. So this is So what we have is we define our curvature, so that's the definition. So for every of these valuations, so A is a functional, like one of these eigenvectors which we have looked at, a valuation. Valuation is just like counting triangles, counting edges, counting, these are all valuations. The other characteristic is a valuation. A valuation is something which behaves like inclusion, exclusion, like counting, and the small vk are the basis for the valuations, and also these barycentric characteristic numbers are the basis for the valuations. This is a discrete Hardinger a result. But if you have a valuation like that, we can, so this is a vector, right? And then we can look at the curvature, so define, so fine. First of all, there is an invariant. It's functional xa of g, which is just a dot with b of g. We have seen that, right? If these are the eigenfunctions of eigenvectors of the matrix AT, of this barycentric refinement matrix, then these are the barycentric characteristic numbers. In a special case, when we take the first eigenvector, we get the Euler characteristic. So these are the, so if you have that, we can define a curvature. Curvature, which is a local number attached to every vertex. So it's k, x. Let's just write here x, capital X. So this is what this is. It's a sum, k equal to 0 to infinity, goes there only finitely many summons there, and then we take the ak, then we take the vk, and then we divide by k plus 1. Vk minus 1, and then divide by k plus 1. So you see here, it's essentially what we have is, if you take the if A is just 1 at the kth entry and everywhere else 0, then the fundamental theorem of graph theory gives us immediately already a Gauss-Bonnet result. But this is the curvature, and then we have Gauss-Bonnet. Let's call this Gauss-Bonnet germ. So Gauss-Bonnet, this is two-dimensional classical. Germ did it in higher dimensional. First intrinsic proof of the Gauss-Bonnet germ theorem in higher dimensions, and I add here Levitt because this is as far as I know, the first who did a discrete version, not as general as here, but case of Euler characteristic. I discovered this a couple of years ago. Actually, I found this reference only very recently. And so the thing is that the x of g is the sum x v of k x. So these curvatures add up to the characteristic. Especially in the case of the Euler characteristic, we have the classical Gauss-Bonnet. If you would take a triangularization of a manifold and make this finer and finer, you would get to the Gauss-Bonnet theorem, which is quite complicated in the continuum. But this is the thing, and if you look at it, it's kind of pretty obvious, right? Because the sum of x, if you take divided by k plus 1, this is vkx, and then you have just to sum this up. You know, valuations are linear space, so you can add this up. So that's Gauss-Bonnet. So the strategy will be to actually show that this curvature is located on the boundary of the manifold. So that's pretty physical, right? So the actually gets even more physical if we write the curvature as an expectation of indices of a. So that's what we do next. So this is Gauss-Bonnet. That's one part, and it was almost trivial in the graph theory case. Can't believe how many times this has been rediscovered in the two-dimensional case. And two-dimensional case is more than 100 years old. For everyone has looked at this in the context of graph coloring, especially the four-color theorem, where curvature plays a role. Maybe I just should mention this. This is kind of also historically important. So if you take two-dimensional case, so what is the curvature in the two-dimensional case? We have 1 and then minus, so kx. This is the vertex x. So it's 1 minus, and then we have v0, that's v minus 1, v0 over 2 plus v1 over 3. Now it stops here because we have no tetraeder, and so this is v1, that's actually v1 is the degree of x half plus the degree of x over 3, which is 1 minus degree of x over 6, which is the classical formula which has been known for 130 years. And this formula generalizes this. The curvature is that if you have more than 6, then it's negative curvature. If you have less than 6, that's what was interesting. People were interested in positive curvature parts here in the case of the coloring. If you look here, it's very interesting, kind of on the barycentric subdivision. So there are positive and negative curvature things. But actually, negative curvature nodes are isolated here. So they're always surrounded by positive curvature or zero curvature parts. But in average, it's flat here. This average is in the limit to a flat because our total curvature here is 1 by Gauss-Bonnet. So so this is Gauss-Bonnet, and now we have to look at Poincaré-Hopf. So Poincaré-Hopf deals with functions on the vertex set. Let's just call this set of functions omega. So these are all scalar functions on the zero forms on the graph, and if you want to think about them as waves, so these are functions. And what one can look at is one can look at the index for this function. So let's define E. So if you have a evaluation, and so a functional x is a functional given by a evaluation, you can look at EFX attached to a vertex x, which is x of bx minus x of bs me just explain what this means. So this is a Bfx is the part of the unit ball where the function is smaller than f of x, and this is part of the unit sphere where the function is smaller. So if you look at that, and if you have I mean, this definition is made in such a way that you actually see immediately that E f x x E f x of x is x of g. Because you just build up the graph more and more, you add more and more, use the property of the valuation. So this is Poincare-Hopf. Now, in the case of Euler characteristic, this is just one, and this is the Euler characteristic of the part of the sphere which is smaller. So this is a special case, and then you have really kind of a situation very similar to the Poincare-Hopf in the classical. If you take a discretization and you take a function, and you get the same index. So we have this. These are, what is important, these are indices now. These are E f x. These are divisors. These are integer valued functions on the vertex set. And so we have this Poincare-Hopf. Now what is very nice is that if you take a measure, so it's a probability measure, also these, I mean, by the way, I experimentally, found in the case of Euler characteristic by just, doing thousands of experiments and just see what works. So this is a probability measure, and also this next result, which is integral geometry, was experimentally found. So it's a probability measure on omega. So what you do is now you average all these indices. So indices. So E is the expectation. Now you can look at the expectation of this index E f x, and that's another theorem. So the closest I found here is in the continuum in the case of polytopes is by Banchoff, a result which is this gives curvature. Under mild conditions, you can take, for example, all colorings with all locally injective functions, and which take finitely many values. You can take IID random variables which are continuous. So this is pretty general, and it actually shows that the integral, the expectation of Poincare-Hopf is Gauss-Bonnet, and this allows you also to prove or state Gauss-Bonnet in the continuum. So you have the manifold, and you take a probability space on functions, and for example you embed it in a higher dimensional manifold, and then you look at critical points, and then you get the critical points. You attach indices like plus indices or minus indices. And the average of the plus images, if you make an expectation of all possible functions, kind of all possible linear functions in a surrounding ambient space, for example, you get here positive curvature, negative curvature, you get the usual curvature. Still don't know how to get, in general, the usual curvature intrinsically, and heat signature functions are probably a good candidate for that, where the manifold itself is the probability space. So you start heat going at some point, and you get critical points, and you average over the whole manifold, and you look what happens, and you get curvature. If you don't get curvature, you still have Gauss-Bonnet, but you have another curvature. And so integral geometry allows you to look at different geometries, just depending on the probability measure, which is very nice. And that works also here in the discrete. It's not so difficult to prove, and I want to skip this and look further. So there is another thing. So what we actually show here is we introduce another. So if you look at the average of IFX plus IF minus X divided by 2. This is symmetric index. So what happens in 3 manifolds, for example, if you look at the symmetric index, it's always 0. And so you already kind of have a proof that curvature is 0. And that was my approach also in the graph theory case, to show that curvature is 0. That's what we do here also, to show that curvature is 0. It's enough to show that this symmetric index is 0. Now, what we can do is we can relate the index with a smaller, let me just write this. We can write JF so what we can do is we can, 2 times J, we can write this as the functional evaluated Bx, it's a unit ball, plus, this is just a property of valuations, this exclusion principle, and then we have minus x of Sx, the unit sphere, and then minus x, and here's the interesting part, which is Rfxx, where Rfxx is, that's the level surface, all y, f of y is equal to fx. This is just notation. I have to say what this is in a graph. So what we have, let me just give you the picture. So this is a level surface in S of x. So this is a d minus 2 dimensional d minus 2 graph if G was a D graph. So if you take these two things together, and by the property of evaluations we get this plus this, and if we take the sphere, if you look at the sphere, that's the same thing. For the sphere we get just the total sphere and then the intersection part, which is this surface. What happens is that this graph here is a nice d minus 2 graph. Now we can look at different cases. That's a discrete SAR theorem, which tells that this is a nice d minus 2 dimensional graph. What happens is that the in the case of the Euler characteristic, every ball in the Euler characteristic has Euler characteristic 1. We get here 2, and then in this case this is either 0 or 2 depending on the dimension. For example, if the graph is odd dimensional, then this is even dimension is 2, and that cancels out. We just get the Euler characteristic of a d minus 2 dimensional graph. And now what happens if we average this? If we use induction, this d minus 2 dimensional graph has 0 Euler characteristic. In the case k bigger than 1, where we have not Euler characteristic, then this part is 0, just by the properties of these barycentric characteristic numbers. This minus this is 0 because the curvature lives on the boundary. So that goes away, and we see that it's minus the characteristic for d minus 2 dimensional graph. And then by induction again, if this was 0, also the symmetric index is 0. If the symmetric index is 0, the curvature is 0. The curvature is 0, the characteristic is 0. But this is the proof. It's an inductive proof, and it shows that these barycentric numbers are maybe also physical interest, because what you have here, you think about this as like charges. What happens if charges, if you have a manifold with boundary charges, happen to be concentrated on the boundary. So, what happens in the special case of the Euler characteristic is that this level surface is kind of if you take a four-dimensional graph, the level surface is in the unit sphere is two-dimensional, so you get two-dimensional graphs, and so this index is Euler characteristic of a two-dimensional graph, and the Euler characteristic of a two-dimensional graph is a sum of curvatures on this two-dimensional graph, which means if you average over all possible function, which means you actually average over all possible sectional curvatures in some sense in the graph. So it shows that the Euler characteristic in some sense is very much like the Hilbert action, that you have the scalar curvature you average